Yesterday we discussed the Gauss's law. Now we are going to see some applications of the Gauss's law. Okay. So what are applications of Gauss's law? To find out the electric fields due to various objects. Okay. Let us find out the electric field due to a wire. Okay. So let's see first application, the electric field due to infinitely long charged straight wire. All right. So electric field due to infinitely long charged straight wire. So let's suppose that we have an infinitely long charged straight wire. So this is just an idealization. Okay, we have very long straight wire and there is some positive charge. There is some positive charge. I'm sorry. There is some positive charge uniformly distributed all over the length of this wire. All right. So charge plus Q is uniformly distributed all over the length of this wire. And we want to find out its electric field at some perpendicular distance. Let's call it small r away from it. Okay. So this is our point where we want to find out the electric field. Suppose this one is the point where I want to find out the electric field due to this charged wire. So how do I proceed? So we'll make use of the Gauss's law. Okay, we'll use the Gauss's law to find out electric field. See how. So to apply Gauss's law, we draw a closed surface known as Gaussian surface. Okay, so here symmetry of this wire tells us that the Gaussian surface has to be a cylinder. Okay, it has to be a cylinder. So let us draw a cylinder. So I have drawn this cylinder which is symmetric to the shape of this wire, and this cylinder I have drawn to apply the Gauss's law. Okay, so this is known as the Gaussian surface. This is known as the Gaussian surface. So why do we need a Gaussian surface? Because Gauss's law tells us that the flux due to the electric field Gauss's law tells us that the flux due to the electric field out of any closed surface is equal to algebraic sum of charges enclosed by the surface. Gauss's law tells us the flux due to the electric field out of any closed surface is equal to the algebraic sum of charges enclosed by the surface. Okay, this is the Gauss's law. So Gauss's law is applicable to the closed surfaces. So to apply the Gauss's law, we need a surface, a closed surface, and that's why we draw one. Okay, so that surface is known as the Gaussian surface. Okay, because we are going to use the Gauss's law. All right. So now suppose Q is the total charge on the wire, total charge on wire, and L is length of this wire. L is length of the wire. Then for linear objects, we define a term for continuous charge distribution known as linear charge density. The term is known as linear charge density, right? Lambda equals to charge divided by length. So now, if suppose this Gaussian surface has length small l, let's call the length of this Gaussian surface to be small l. Then how much would be the charge enclosed by the Gaussian surface? So let's suppose Q is the charge enclosed by a Gaussian surface, charge enclosed by a Gaussian surface, by a Gaussian cylinder. So how much would be that? Now since the charge is uniformly distributed, continuously distributed all over the length of this wire, what we can say is the charge will be equal to what? Lambda multiplied by L. So suppose we consider length small l of the wire, charge enclosed would be how much? It would be lambda multiplied by L, right? So Q is equal to lambda times small l. This is the charge enclosed. All right. Now after that we'll find out the flux, right? So see now electric field due to this wire would be like this. It would be perpendicular. It would be perpendicular to the length of the wire. Okay. How? So let me explain this. See, now what we are going to do is we are going to find out the direction of electric field due to this wire. All right. So suppose we have this point P. We have the point P at some distance away from the wire. Then now let's consider a length element, small section of this wire. So this section has length dl. So it will have some charge dq, right? And this charge dq will produce its electric field at point P, right? So this charge dq produces its electric field at point P, and that electric field is suppose dE bar. So this dE bar is directed like this. Okay. So now this is the perpendicular distance of point P from the wire. Okay. So this much distance is suppose small r. Now see, we have considered a small length element above this point O. We can consider same length element, not same, the length element having equal length below this point O at the same distance. So let's consider a length element here which is at the same distance from point O, okay, below point O. So it will also produce its electric field. It has also charge dq. This has this has got charge dq. So it will also produce its electric field at point P, right? So it produces its electric field at point P, but it will be directed like this. It will be directed like this. So let's call this electric field d dash bar. Now what will happen? So if we consider this electric field due to this length element above the point O at certain distance and electric field due to this length element below the point O at the same distance, then they are directed like this. So if lengths of these length elements are equal, then the electric field due to them would be equal because charge on them are going to be equal, right? The electric fields due to them are going to be equal. So this one, d bar dash and d bar, they have same magnitude. Okay. So now we can find out the resultant electric field due to these two. So how much would be resultant electric field? For that, let's consider this angle to be theta. So this angle is going to be theta. This angle is also theta. Why? Because this angle is theta, right? These two triangles would be congruent. Okay. See, this distance is same. This is right angle, this is right angle, and this side is common. So these two triangles are congruent, right? By SAS test. So these are corresponding angles of congruent triangles. So these two triangles, sorry, these two angles are equal, and these are opposite angles for these two angles. Okay, what do I mean by opposite? What is it called? Okay, so we know this angle is equal to this angle and this angle is equal to this angle, right? So now these angles are theta and theta. So we can resolve d bar dash and d bar. So what do we get? So if we resolve them, so components of d bar and d bar dash which are directed vertical in vertical direction. Okay. So these components will be d dash sine theta and d sine theta. D sine theta. So these components they get cancelled out because d bar dash and d bar they have same magnitude, right? But these components are directed opposite to each other. Okay, so they get cancelled out and the net electric field due to these two length elements will be in this direction. Okay, so how much would be net electric field? It will be addition of the horizontal components of d bar and d bar dash. So it is d dash cos theta plus de cos of theta. So this wire has infinite length and we just considered only two small length elements on this wire. Okay. So now we can consider another length element here. So for every length element that you consider above the point O, you have a length element having equal length below the point O at the same distance. So the vertical components of electric field due to them will get cancelled out and electric field will be directed. So the horizontal components they get added and that's why the electric field is directed like this. Okay. So it is directed along perpendiculars to the length of this wire. Okay, towards point P. That would be the direction of net electric field. Got it? If you take point P on this side, if you take it on this side, then direction of electric field would be like this. Okay. All right. So after that, see, now we want to find out the flux. Okay, we want to find out the flux due to the electric field of this wire through this Gaussian surface. So for that, we'll consider three parts of this Gaussian surface. One part is this one part is this one, okay, and one part is this one. Okay, what do I mean by this one and this one? So one part is the top surface, another is the bottom surface, and third part is curved surface. So we'll break this Gaussian surface into three parts. Okay, so let's call this surface surface 1, this one as surface 2, and this one as surface 3. So now the electric field is directed. If you consider any point, you consider a point on this surface also. Okay, if you consider a point on surface 1, suppose, so this is the point on surface 1. Will the electric field lines pass through that point? So how will the electric field line pass through that point? So electric field line will be directed like this. Okay, electric field is directed like this. Okay, so it will pass through the point, but it will not pass through the surface 1. Okay, it will never pass through surface 1. And also for surface 3 also, if you take some point, electric field will be directed like this, perpendiculars to the length of the wire. Okay, so electric field will pass through that point, but it will not pass through surface 3, right? So how many number of electric field lines are passing through surface 1 and 3? No electric field lines are passing through surface 1 and 3. So flux through 1 and 3 is 0. Okay. And the flux through this area, okay, this curved area if you consider. So we know that area vector is perpendicular to plane of the area. So if you consider small surface area, so if I consider a small surface area here, point P, which is part of the curved surface, what will be the direction of area vector here? Direction of area vector is like this, perpendicular to plane of area. So suppose this small surface is ds. So the electric field at point P, it is directed like this. Area vector is also directed in same direction. So electric field and area vector, they are directed in same direction. Okay. So now let's find out the flux. So flux through Gaussian surface. We want to find out. So let's call it phi. So it is equal to phi 1 plus phi 2 plus phi 3. Right? So phi 1 is flux through top surface. Phi 3 is flux through bottom surface. Okay, and phi 2 is flux through this curved surface. So flux through surface 1 and 3 is 0, as we have discussed. So it will be phi 2 only, because phi 1, since phi 1 and phi 3 are 0. Why are they 0? Because since E bar and A1 bar and A3 bar are perpendicular to each other. Since they are perpendicular, the dot product of electric field and area vectors are 0. And that's why flux through those surfaces are 0. Got it? Alright. So ds is small part. It is small part of A2. Right? Okay, instead of 1, 2, 3, let's call them A1, A2 and A3. Okay. So ds is small part of the curved surface 2 whose area is A2. Okay. So flux through ds, flux through ds, let's call it d phi, it's equal to E bar dot ds bar, right? And since they are directed in same direction, since E bar and this ds bar, they are directed in same direction. Okay, we know that the direction of area vector is perpendicular to plane of area. So since electric field at point P and this area vector, they are directed in same direction, so the angle between them is 0. So we have E bar dot ds bar is E multiplied by ds multiplied by cos of the angle between them, and cos of 0 is 1. So it is just equal to E multiplied by ds, right? So then, therefore, net flux, what would be net flux? Phi is just equal to phi 2, okay, as we have discussed. So it will be integral of d phi, and that is its integral of E multiplied by ds. Okay. So now see what of which of these two is a variable and which of these two is a constant. So if you consider that curved surface, so each point of curved surface is at the same distance. Each point of this curved surface is at the same distance from the wire, right? If you consider the curved surface, the cylinder, then this wire is along the axis of the cylinder. Okay, so each point on this wire, each point on the cylinder, it is at the same distance from the wire, right? So since if you take each point is at same distance, therefore it doesn't matter if you take point here or here or here, electric field at all those points would be equal. Electric field at all those points would be equal. Why? Because wire has infinite length. Okay, so wherever you take your point P, the electric field through that point will be what? Perpendicular to length of the wire only. Okay, so we can say that E is a constant. We can take it outside. So it is E multiplied by integral of ds. What is the integral of ds? Integral of ds means you take small surface areas like this on this curved surface, okay, and add those all areas. So what do you get? You will get total surface area of the curved part of the cylinder, okay, and that is, what is the surface area of the curved part of a cylinder? it is 2 pi r L, right? Okay, 2 pi r multiplied by L. This is the formula. So this is the flux. Okay, and then we can use Gauss's law. So using Gauss's law, what can we say? That this flux is equal to charge enclosed divided by epsilon naught. How much is charge enclosed by the cylinder? Small q. Small q divided by epsilon naught. So it is E multiplied by 2 pi r L is equal to small q divided by epsilon naught. And what is small q? So small q is equal to linear charge density multiplied by L. Okay, small l. Lambda times L divided by epsilon naught. This L and L gets cancelled out, and what do we get? The electric field due to a wire, an infinitely long charged straight wire. The electric field is given by lambda divided by 2 pi epsilon naught r. Okay, 2 pi epsilon naught r. So this is the formula. And what is direction of this electric field? So if you want to write it with direction, then it is perpendicular to length of wire. Okay, it is perpendicular to the length of wire. Okay, so you can say it's directed along r cap. Okay, or for perpendicular you can write a unit vector n cap. N cap means it is perpendicular to length of wire. Okay, n means normal. Okay, n means normal, right? So this is the electric field lambda divided by 2 pi epsilon naught r, and we'll write it in a vector form. All right. In vector form, E bar is equal to lambda divided by 2 pi epsilon naught r multiplied by n cap. N cap means a unit normal vector. Got it? After that, let's find out the electric field due to an infinitely large straight charged sheet. Charged infinite sheet. Okay. Once again, infinite. So we have very large plane sheet, and it is uniformly charged. And we want to find out electric field due to that plane charged sheet. So let's draw that sheet first. So this is the charge, capital Q. It is uniformly distributed all over the area of the sheet. So what do we have to do here? If charge is uniformly distributed on the area of the sheet, we can define a quantity known as surface charge density. Okay, so we are interested in finding out the electric field due to this charged sheet at this point. This is point P. Okay, so now here again we are going to use Gauss's law. So to use Gauss's law, we need a surface known as Gaussian surface. Okay, so here we draw a Gaussian surface. Once again, we draw a Gaussian cylinder. Okay, so now this point P is at some distance from the sheet. See, can you imagine this? This cylinder, half of the cylinder is on this side. This is charged plane sheet. Half of the cylinder is on this side of this charged plane sheet, and the remaining half is on the other side. Okay, so the cylinder, the Gaussian cylinder, it is penetrating that charged plane sheet, right? So you take this point which is at some distance, let's call this much distance equal to A. Okay, then you take another point, let's call it P dash, which is on other side of the sheet. Okay, the P dash, it is on other side of the sheet, and you draw a Gaussian cylinder which passes through the sheet. Half of the Gaussian cylinder is on this side, remaining half is on other side, right? Okay, so now we want to find out the electric field due to this charged plane sheet at point P. So once again, now we can imagine this. The electric field will be directed like this, perpendicular to the plane of sheet. So do I need to explain this, or is it clear that electric field will be directed perpendicular? If you have charged plane sheet like this, electric field will be directed like this, perpendicular to the plane of this sheet. Okay, passing through that point P. Okay, and on this side, because this is positive charge, so on other side also the electric field lines due to that positive charge will be radially outwards, perpendicular to the plane of the sheet, and the electric field lines, they will go on this side as well as on the other side, right? So if you consider the flux through this Gaussian cylinder, and once again if we consider three parts, so if we consider this area A1, this area A2, and curved area is suppose A3. Okay, so A1 and A2 are flat areas of Gaussian cylinder, and A3 is the curved area. A3 is curved area. So now electric field lines will pass like this. Okay, so electric field lines, they will pass like this, perpendicular to plane of the sheet. That means now in this case, no electric field lines are passing through the curved area. Okay, they are only passing through the flat areas of the Gaussian cylinder. Okay, yes, no? So now since the electric field is uniformly distributed, sorry, since the charge is uniformly distributed all over the surface area of the sheet, therefore we can define the surface charge density. And what is surface charge density? It is charge divided by area. So Q is total charge, A is total area of this sheet. Okay. So then now see, the field lines through this surface, they are due to this much charge only. Okay, they are due to this much charge only, charge on this area only, right? Or how much is the charge enclosed by this Gaussian surface, by this Gaussian cylinder? Only this much charge. So if this is a sheet and this is your cylinder, how much is charge enclosed in it? Only charge in that much area, right? Only charge in this much area, because the cylinder penetrates through that much area only. Okay, so that much is the charge enclosed. So let's call that charge as dq. dq is the charge on that surface. Okay, dq is the charge on that surface. So how much would be charge? So this area is suppose ds. Okay, this area is suppose ds. So charge enclosed is suppose dq. It's equal to sigma multiplied by ds, right? Because charge is equal to sigma, the surface charge density, multiplied by area. Okay. After that, we can use the Gauss's law. So Gauss's law tells us, okay, flux through this Gaussian surface, flux through Gaussian surface, Gaussian cylinder let's call it phi. So it is equal to what? Charge enclosed divided by epsilon naught. It's equal to charge enclosed dq divided by epsilon naught. Now, how much is phi? So phi is equal to phi 1 plus phi 2 plus phi 3. And what is phi 1, phi 2, phi 3? It is flux through this area A1 plus flux through area A2 plus flux through this area, the curved area. Okay. So no flux is passing through the curved region because electric field lines are perpendicular to the surface area of curved region. So if you take any small surface on the curved region, what would be direction of the area vector? It is perpendicular to the plane of area. So its direction will be like this. And what is direction of electric field lines? It is like this, perpendicular to plane of the sheet. Okay. So no field lines are passing through curved region. Okay. And that's why what is area of curved region? It's A3. So phi 3 is 0. Phi 3 is equal to 0 since A3 bar and E bar are perpendicular, right? And then this area A1 and area A2 is equal to this much area. Okay. And what is that area? I'm sorry. What is that area? This area is ds. Okay. And what about the area vector? So this area vector here will be directed like this. Okay, this is A2 bar, and the electric field will be also directed like this. Will also be directed like this. Okay. So if you consider the sheet, the electric field will be perpendicular to plane of sheet. Okay. At this point, what is direction of area vector? So we discussed this yesterday, that the area vector for a closed surface is considered as in direction of outward normal, outward perpendicular. So here the area vector will be directed like this. Okay, so this is the direction of area vector. Okay, A1 bar, and again electric field is also directed in same direction. Okay, so what's the angle between electric field and area vector? It is 0. The angle between electric field and area vector is 0. And therefore, what we can say is flux through area A1 is equal to electric field multiplied by area A1 plus flux through area A2 is electric field multiplied by A2, and A1 and A2, they are equal. They are equal to this area only, area enclosed, right? So it is E times ds, you can say, plus E times ds, or you can say it is 2 times EDS. Okay, that's the flux. And it is equal to what? Using Gauss's law, it is equal to dq divided by epsilon naught. So this is flux, and using Gauss's law, this is equal to dq upon epsilon naught. And what is dq? So dq is equal to sigma times ds. Right, dq is equal to sigma times ds. So it is sigma multiplied by ds divided by epsilon naught using Gauss's law. Okay. So this ds and ds will get cancelled out. You take 2 on the other side to get the electric field. So you get electric field E is equal to, therefore you get electric field E is equal to sigma divided by 2 times epsilon naught. Okay, this is the electric field due to an infinitely large charged plane sheet. Okay, and what is its direction? It is in direction of normal, outward normal to the plane of sheet. Okay, so in vector form, you can say E bar is equal to sigma divided by 2 epsilon naught multiplied by n cap. Got this? Is it clear? Electric field due to uniformly charged thin spherical shell. This is what we are going to find out now. So let's suppose that we have a spherical shell like this, and the spherical shell has charge capital Q uniformly distributed all over its surface area. Okay. So this is a spherical shell. It means that it is hollow, right? It's hollow. There is no mass or no charge inside the shell. Okay. The shell is empty. Inner surfaces, sorry, inner portion you can say it is empty. Okay. So now we want to find out the electric field due to this shell. So now here there will be 3 points that we need to consider. One will be a point inside the spherical shell, a point on the spherical shell, and point outside of the spherical shell, right? So charge is capital Q. So first of all, let's consider a point inside the spherical shell. Okay. So I will draw a Gaussian surface first. Okay. So let's suppose I want to find out electric field at this point P, which is inside the spherical shell. Okay. So tell me how much would be the electric field? All right. So see, suppose Q is charge on the shell and R is radius of the shell. So radius of the shell is this much. This is R. This point is O, center of the shell, right? So R is radius of the shell. So now the charge is distributed all over the surface area of the shell, uniformly distributed. Okay. So for this continuous charge distribution, because it is distributed all over the surface area, we define a quantity called as surface charge density. Density. Right. So surface charge density sigma is equal to charge divided by surface area Q upon A. And how much is area of a sphere? Area of a sphere is 4 pi r square. So it is Q divided by 4 pi r square. Okay. So after that, so let's consider point P, which is inside the spherical shell. Inside the shell. Okay. So for this point P, if we consider a Gaussian surface that I have already drawn, so considering the symmetry of the problem, Gaussian surface would be a sphere only, right? So I have already drawn the Gaussian sphere. This is Gaussian sphere or Gaussian surface. Okay, right? So how much is the charge enclosed by the Gaussian surface? How much is charge inside that Gaussian surface? Zero, right? There is no charge inside the Gaussian surface. Okay, so I can say flux, okay, which is E bar dot ds bar, and okay, let's write flux phi only first. Phi equals to what? Charge enclosed divided by epsilon naught, right? And since charge enclosed is 0, since charge enclosed is equal to 0, and therefore I can say flux is 0. Okay, so flux through this Gaussian surface is 0. That means no electric field lines pass through the point P, and if no electric field lines pass through the point P, that means electric field at point P is 0, right? Therefore, I can say no electric field lines pass through point P. No electric field lines pass through this Gaussian surface means through the point P. Therefore, electric field at P is equal to 0. Okay. So what does that mean? If you have a charged, charged closed surface, okay, charged closed surface, the electric field inside that charged closed surface would be equal to 0. I'm sorry. So electric field inside the charged closed surface is equal to 0. Okay. So does the shape of that surface matter? Should it be spherical only, or can it have any shape? You take some surface like this, right? This is a hollow surface having this kind of a shape. So there is some charge uniformly distributed all over this surface. How much would be the electric field at any point which is inside this surface? This is point P. So electric field inside this surface would be 0. Okay, electric field inside this surface would be 0 at any point. Okay, uh, does the location of point matter? Where that point is inside the surface? It doesn't matter. Okay, where is the point inside the shell? Does it matter? It doesn't matter, right? If point is here, I can draw a Gaussian surface passing through this point, which will be like this. Still there are no charges enclosed. That means flux would be still 0. Okay, so it doesn't matter where is that point inside the spherical shell. Everywhere the field will be 0. And also the shape of this surface doesn't matter. Okay, so it doesn't need to be a spherical shell only. It can have any surface. If you consider any closed surface of any shape, still the electric field inside that closed surface would be equal to 0. Charges distributed on the surface. You got it? Yes, no? Now, let's suppose our point P is just outside. You can see the point P is just on the surface. Okay? The next is point P is on surface of that spherical shell, on the surface. Then now whatever is the spherical shell, it's the Gaussian surface also, because point P is on the surface itself, right? So now how much would be the charge enclosed? Okay, before that, let's consider instead of P, let's take some other point, P, Q, R, not R, S, T. Let's suppose point T is on the surface. Okay, this is the point. So now what will be the direction of electric field due to this spherical shell? So once again, we can argue in terms of the components of electric field due to all small sections, and we'll find out that electric field will be directed radially outwards. Okay, so this will be the direction of electric field. It will be radially outwards. This is E bar. And here, this is my point T. So I will consider small area around this point T, which is small part of the Gaussian surface. So let's suppose this much area. Let's call it ds. So what is direction of ds bar? Direction of ds bar is also this one. Okay, it is perpendicular to plane of the area, right? So the electric field and ds bar, they are perpendicular to each other. Okay. So now ds bar is small area vector. It's small area around point T. Okay. And therefore flux through ds is what? Let's call it d phi. So d phi is equal to what? It is E bar dot ds bar, and because E bar and ds bar, they are in same direction, so flux is E into ds multiplied by cos of theta, right? So theta is the angle between them, which is 0. So cos 0 is 1, so it is equal to E multiplied by ds only. This is the flux. Okay, and therefore we can say net flux through the Gaussian surface passing through point T. So what will be Gaussian surface passing through point T? It is another sphere. Okay, another sphere which overlaps with this spherical shell, right? Because point T is on the spherical shell itself. Okay, so it is equal to, so flux is equal to what? It is integral of d phi, and now this point T on the spherical shell, it is not spatial. Okay, you can take any point anywhere on the spherical shell. For any such point, the electric field will be directed what? Radially outwards through the point. And if you take area around that point, okay, any area around that point, then the area vector and the electric field will be directed in same direction. So the electric field on this surface is constant in magnitude. It has different direction, but it is constant in magnitude, right? So d phi is E multiplied by ds. E we can take outside, so it is just E multiplied by integral of ds over the Gaussian surface. Over Gaussian surface. Okay, I will not write this. It's understood that it is over the Gaussian surface. So what is this integral? Integral of ds is total area of the Gaussian surface. And now our Gaussian surface is the spherical shell itself, right? So this is equal to, so it is equal to E multiplied by surface area of spherical shell, which is 4 pi r square, right? So then we can make use of Gauss's law. Okay. So Gauss's law tells us that the flux is equal to charge enclosed divided by epsilon naught. And now how much is the charge enclosed by this surface? Tell me. It's the total charge on spherical shell, right? So this phi is equal to total charge on spherical shell q divided by epsilon naught. I'm sorry. Okay, and therefore this flux is equal to what? E multiplied by 4 pi r square, which is equal to q upon epsilon naught, and therefore electric field is just equal to what? Take that 4 pi r square on other side, so you can write this as 1 upon 4 pi epsilon naught multiplied by q upon r square. So this will be the electric field. This is electric field on the spherical shell, okay, on any point on spherical shell. So you can say for the points on spherical shell, the shell acts just like a charge which is at the center of the shell. Okay, so the shell acts as if there is a charge kept at center of the shell. Center of the shell, charge of equal magnitude is kept at center of the shell. Okay, so then we considered point inside the shell, point on the shell. Next is point outside the shell. Okay, so let me draw shell again. So this is the shell, and now we will consider point outside the shell. All right, so this is our shell, and radius of the shell is r. Now I consider some point PQRST point. Okay, let's call it A. Okay, so point A is outside the shell. It is at distance small r from the center of the shell. Okay, I'm sorry. Okay, so now you consider any point on this Gaussian surface. So I have already drawn the Gaussian surface, which is again a sphere. So I can call it Gaussian sphere. So for any point on this Gaussian sphere, the electric field will be the electric field will be directed like this. Okay, the electric field will be I'm sorry. The electric field will be directed perpendicular to the plane of that surface. Okay, perpendicular to the surface, right? So if you take small surface, small area around point A, then the area vector and the electric field, they will be directed in the same direction. Okay, so this is direction of electric field also. This is direction of the small area vector also. This is ds bar also, right? Direction of ds bar also. So for point outside of shell, which is at distance r away from the center of the shell, we can say that what? Let's suppose ds is the area, small area. Ds is small area around that point. Okay. Then the now ds bar and e bar is in same direction. So flux through ds, flux through ds. Okay. So it is, let's call it d phi. D phi is equal to what? E bar dot ds bar, and since they are in same direction, it's just equal to E multiplied by ds, right? Therefore, flux through the Gaussian surface passing through point A. So flux through Gaussian surface, passing through A, flux through Gaussian surface is phi equals to integral of d phi, and it is equal to integral of E dot ds. E you can take outside, so it is integral of ds. So which is equal to what? Total surface area of the Gaussian sphere. So it is E multiplied by 4 pi r square. That's pi, right? And then what is this flux? So this flux is equal to, according to Gauss's law, I is equal to charge enclosed divided by epsilon naught. And how much is charge enclosed? Charge enclosed is equal to Q actually, right? So now we'll find out two different formulae. So first I will write charge enclosed is equal to sigma surface charge density multiplied by the surface area of sphere. Okay, so it is sigma multiplied by A surface area. Okay, so point is also A. Alright, so surface area is 4 pi r square, right? So it is sigma multiplied by 4 pi r square. This is the charge. So then what is phi? Phi is equal to E multiplied by 4 pi r square. It's E multiplied by 4 pi r square. 4 pi and 4 pi gets cancelled out. So we get formula for electric field. It's equal to sigma r square upon epsilon naught small r square. Okay. So electric field at a point which is outside, electric field at a point which is outside the surface of spherical shell, it is equal to what? Sigma, the surface charge density, multiplied by r square. R is radius of the spherical shell, divided by epsilon naught multiplied by r square. What is the small r? It is the distance of the point from the center of the shell, right? So we can write it like this. Okay, this is one formula. Then we can substitute sigma. So sigma is equal to what? Charge upon, or instead of doing that, I will just substitute charge enclosed is equal to Q, capital Q. Total charge is enclosed by this Gaussian sphere, right? All the charge is inside the Gaussian sphere. So if you use that, okay, then you get E multiplied by 4 pi small r square is equal to Q upon epsilon naught. So that means E is equal to, once again, 1 upon 4 pi epsilon naught multiplied by Q upon r square. So once again, you can say for a point which is outside the spherical shell acts as if there is a charge equal to charge on the shell kept at the center of the spherical shell, right? So electric field is just electric field of a point charge, 1 upon 4 pi epsilon naught multiplied by Q upon r square. What is r? Distance of point P, point from the center of the shell. Okay. Okay, so we'll take 10 more minutes and we'll see one more application. Okay, so now let's see electric field due to a solid sphere. Okay, electric field. We saw electric field due to a spherical shell. Next, let us see electric field due to a solid sphere. Okay, so now the charge is uniformly distributed all over the volume of the sphere. So here, I'm sorry, this is a solid sphere. And how is the charge distributed? It's all over the volume of the sphere, right? And its radius is suppose capital R. This is the center. You can call it O. Radius is capital R. Okay. So Q is the charge distributed in the sphere. It is in the sphere. Right. That's the difference. This is solid sphere. So there is mass inside the sphere, charge uniformly distributed inside the sphere. Okay. R is its radius. So now what do we have to do? We have to define a quantity corresponding to this case. So if charge is distributed in the volume, what do we define? We define the volume charge density. Okay. So what is volume charge density? Rho charge divided by volume of the sphere. And what is volume of the sphere? So it is 4 by 3 pi r cube, right? 4 by 3 pi r cube. Okay, so then let's consider a point which is inside the sphere. Okay, so let's consider a point which is inside the sphere. So let me draw a Gaussian surface. I'm sorry. All right. So this is suppose point P, which is inside the sphere. Okay. This is point P, and it is at distance small r. Can you see this? It's at distance small r. I will zoom this diagram. Okay. So point P is at distance small r from the center. So now once again we can say the electric field will be radially outwards, right? So if we consider a small surface area around this point R, sorry, around the point P, if we consider a small surface area, then the electric field and that surface area ds, they will be directed the same direction. Okay, this is the direction of E bar also. This is the direction of ds bar also, right? Okay, so then I can say flux through this. Okay, so let's suppose for point inside the sphere. So ds is small surface area around the point. Around the point. Which point? Point P. So therefore d phi is flux through this surface area. So which is what? E multiplied by ds, right? And then flux through total Gaussian surface, which will be a sphere only. So flux through total Gaussian surface phi is equal to what? Integral of d phi, that is integral of E ds. And once again we can say that electric field at each and every point of this Gaussian surface will be equal. So we can take E outside. So it will be, so phi is equal to E multiplied by integral of ds, which is equal to E multiplied by 4 pi small r square. Okay, 4 pi small r square. Now, how much is the charge enclosed? Okay, so this is flux. So using Gauss's law, we can say that this flux is equal to what? Charge enclosed divided by epsilon naught. Now, how much would be the charge enclosed? So it is sigma, sorry, not sigma, rho multiplied by volume of this Gaussian surface. Volume of Gaussian surface. Because now charge is uniformly distributed all over the volume, right? So I can say phi is equal to, what is phi? E multiplied by 4 pi small r square. It is equal to rho multiplied by 4 by 3 pi r cube, small r cube, that is the volume. Okay, volume of this Gaussian surface is 4 by 3 pi multiplied by small r cube, and you have divided by epsilon naught. Okay, then some cancellations will happen. 4 pi and 4 pi will get cancelled out. You can divide this r cube by r square. One r will remain there. So you get E is equal to, what? It is rho, yeah, it is rho multiplied by small r. Sorry, it is rho by 3, 1 by 3, or I can say rho by 3, R divided by epsilon naught, right? Rho by 3 R divided by epsilon naught, because 4 pi and 4 pi will get cancelled. R cube divided by R square is R. Okay, so this is the formula. Got it? Yes, no? Okay, then see, I'm sorry. So now we considered a point which was inside the Gaussian surface. So for that one, E is equal to rho upon 3 small r divided by epsilon naught. Okay, so now we can substitute the value of rho. So what is rho? So rho is 4 by 3. Okay, rho is what? Charge multiplied by 4 by 3 pi r cube, right? You can take this 4 by 3 pi r cube on other side. So rho is, sorry, what am I saying? Rho is charge divided by 4 by 3 r pi r cube. Okay, so it is q divided by 4 by 3 pi r cube. So it is q divided by 4 by 3 pi r cube multiplied by, you have 3 in the denominator. So I have substituted the value of rho, right? So q upon 4 by 3 pi r cube multiplied by this 3, and you have small r in multiplication and epsilon naught in the denominator. So this 3 and 3 will get cancelled out. So you get one formula in terms of q, the charge. Okay, so it is 1 upon 4 pi epsilon naught, right? I can write 1 upon 4 pi epsilon naught multiplied by this 3 will get cancelled out, multiplied by r upon r cube, sorry, q times r divided by r cube. This is the formula in terms of electric field. Now you don't have to memorize all the formulae, but it can be asked. Okay, so in that case, you just have to substitute the value of rho. So this is simplest formula to memorize. This one is simplest formula to memorize. Okay, so then now a point R, a R is on the surface. Then you can substitute R equals to capital R, and if you substitute that, if you substitute R equals to capital R, what do you get? You substitute R over here, R will divide this R cube and R square will remain in denominator. So for the point on the sphere, the electric field is 1 upon 4 pi epsilon naught q divided by R square only. So then next is point outside the sphere. Okay, so see, even if you consider point outside the sphere, okay, you consider I'm sorry, you take this sphere, charge is uniformly distributed on the sphere, and you take another sphere which is outside, this sphere, but it is concentric to the sphere. Okay, so point P is now outside. What is distance of this point P? Once again, let's suppose distance of point P is small r, right? So again you take small area ds surrounding the point P, then the electric field and this area vector, they will be directed in same direction. Okay, so flux through ds, okay, d phi is flux through ds. D phi is equal to what? It is just E multiplied by ds, and therefore flux through the Gaussian surface. Now Gaussian surface is outside. Okay, so flux through Gaussian surface. integral of this, right? And E will be constant. You can take it outside. Integral of ds is equal to what? 4 pi r square. So you get pi equals to E multiplied by 4 pi r square, right? And this flux is equal to charge enclosed divided by epsilon naught. Okay, so this is charge enclosed upon epsilon naught. So Gauss's law tells us that phi is equal to charge enclosed. How much is charge enclosed? Total charge actually. Okay, so it is q upon epsilon naught. So if we substitute phi is equal to E multiplied by 4 pi r square, E multiplied by 4 pi r square, okay, then what do we get? E is equal to 1 upon 4 pi epsilon naught multiplied by q upon r square. Okay, the same formula. So it doesn't matter whether it's a shell or it's a sphere if the point is on the shell or a sphere or outside. Okay, it matters only for points which are inside. So for a shell, electric field will be 0 at inside points, right? And for solid sphere, there will be some electric field inside the solid sphere also. Okay, which is given by this formula. Which formula? This formula, or you can say this formula, right? So you got this? Yes, no? All right. So, okay. So let us stop here.